June 12, 1944. Somewhere near the English coast, the sound of an approaching radial engine cuts through the afternoon haze. The aircraft drifts into view, AP Air 47 Thunderbolt, olive drab and silver, trailing a thin column of smoke. The left wingtip vibrates slightly with each rotation of the propeller. Its undercarriage lowers unevenly, one wheel trembling before locking into place. On the ground, two Republic Aviation engineers step out of the dispersal hut, shielding their eyes against the glare. The fighter's nose bears the dull burn marks of cannon fire. Entire panels of its fuselage are punctured, light pouring through dozens of holes. From the rear quarter, the metal skin appears peeled like torn fabric. The pilot, Captain James S. Calhoun of the 78th Fighter Group, keeps one hand tight on the throttle, the other on the wobbling stick. He is guiding what remains of a 7-ton machine that should not be flying. The plane touches down hard on the pierced steel runway. Its right tire bursts, the aircraft veering slightly before settling. Ground crew vehicles approach, sirens off. The propeller stops with a dry metallic click. For several seconds, the only sound is the cooling crackle of the Pratt & Whitney ARC 2800 engine. Then, with a brief hiss, the canopy slides back. Calhoun raises both hands, gestures to the tail. A crewman shouts, "Flaps intact." Another calls out, "Hydraulics still holding pressure." By the time the Thunderbolt is towed to the maintenance bay, sunlight filters through over 200 holes. Each one is counted. On the left wing root, 37. Across the fuselage spine, 68. The vertical stabilizer, 23. Fragments of 20mm shells are embedded near the oil cooler and around the engine cowling. One armor plate, designed to protect the pilot's back, has absorbed for direct hits. It remains unbroken. Photographs are taken from 4 angles. Technicians circle the entry points in chalk and number them sequentially. A clipboard record notes, aircraft P-47 DR-22RE, serial 42 to 26,545, returned from sortie at 15:17 hours, sustained heavy damage, engine operational. The radial cylinders, arranged in a double row of 9, show uneven wear but no fracture. Oil leaks along the crankcase seam, but pressure readings remain nominal. According to the base log, the aircraft had been part of a bomber escort mission over northern France. It was attacked by at least 4 Focke-Wulf 190s near Rouen. Witnesses reported that the Thunderbolt absorbed repeated bursts from short range before rolling into cloud cover. No further contact was made until it reappeared over the channel. An inspector from the 8th Air Force Maintenance Command arrives within the hour. He runs a hand over the pitted skin near the left intercooler duct. Still sealed, he remarks quietly. Beneath the cowling, the engine's ignition harness glows faintly under a portable lamp. The smell of scorched fuel lingers in the hangar. On the adjacent table lie samples of torn aluminum, armor plate, and plexiglass canopy fragments. One technician measures thickness variations with calipers, 0.032 inches at the damaged panels, 0.080 at the reinforcements. The contrast is precise, deliberate, weight sacrificed only where survivability allowed. By nightfall, the aircraft is partially stripped. 2 crewmen note that every control surface, though perforated, still moves freely under manual pressure. The flight control cables are frayed but unbroken. The oil sump, dented and scarred, still holds its seal. In the inspection notes, a final remark appears in small block letters, aircraft returned to base under own power. Damage estimated, 65% superficial, 10% structural, 25% armor impact. Outside, the runway is dark except for the yellow lamps marking the taxiway. The men roll the hangar door closed. Behind them, the P-47 stands silent under the work light, a machine still holding its shape against the arithmetic of destruction. By morning, the hangar smells of solvent and heated aluminum. The damaged Thunderbolt sits beneath a steel gantry, its skin peeled open like a dissected specimen. Technicians from Republic Aviation and the U.S. Army Air Forces Engineering Division gather around with clipboards and flashlights. Their task is to record not only what broke, but what did not. The first report concerns the engine. The Pratt & Whitney R2800 double wasp, still mounted to its fireproof bulkhead, is rotated manually by hand crank. Despite visible scoring across its cowling, all 18 cylinders compress evenly. One intake valve shows deformation from a 13 mm round, yet combustion integrity remains intact. The chief inspector notes the absence of coolant lines. There is no liquid to leak, no radiator to puncture. The air-cooled radial survives what a liquid-cooled V-12 would not. Each bullet strike is logged by coordinate, wing route, upper fuselage, tail assembly. A map of impact density forms across the airframe, clustered near the oil cooler, sparse at the canopy's rear. Measurements reveal that 78% of hits fail to breach critical systems. The fuel tanks, self-sealing with layered rubber and treated fabric, have absorbed multiple punctures without fire. Crews inject nitrogen to test vapor leakage. The readings stay stable. At one table, a metallurgist examines fragments of 20 mm meningeschos shells recovered from the right wing. Under magnification, the edges show partial detonation, evidence that the thin aluminum skin dissipated energy before the charge fully ignited. Notes are passed to the materials officer. Skin flexibility may act as shock absorber. Nearby, hydraulic lines are pressure tested with a portable pump. Despite two clear entry holes near the actuator housing, fluid loss is negligible. The lines, made from annealed steel tubing, have flattened but not split. Each discovery adds another data point to the aircraft's growing legend. At 0930 hours, an officer from Republic's Long Island plant arrives carrying blueprints. He unfolds the drawing of the P-47's central fuselage. It shows the core frame, for primary longerons, reinforced with heavy-gauge duralumin ribs. The assembly weighs more than an entire Spitfire's wing structure. Engineers trace their fingers along the cross-section, comparing it to the battle-damaged example before them. Overbuilt, one says quietly. Another replies, and because of that, still flying. The P-47's nickname, Jug, had begun as a casual joke, a reference to its blunt fuselage resembling a milk jug. Yet here, the term feels technical. The fuselage's deep belly houses the turbo-supercharger ductwork, forming a natural armor tunnel through which rounds often pass without striking vital systems. Tests on the damaged airframe confirmed this. Several shells entered near the belly scoop, traveled the ducting, and exited cleanly, leaving the machinery untouched. Photographers document the findings for the Republic Aviation News Bulletin. Flashbulbs illuminate the torn wing edges and blackened rivets. In each photograph, the airframe seems both destroyed and intact, a paradox captured in silver nitrate. At midday, a pilot from another squadron walks into the hangar. He circles the Thunderbolt slowly, tracing a finger along one hole-riddled panel. 200 rounds, he mutters. And he brought her home. The technician beside him answers without looking up, 200 we counted. Could be more. By late afternoon, engineers reattach the cowling and reconnect the propeller assembly for a static test. The hangar doors slide open. A ground crewman primes the engine with fresh fuel, steps clear, and signals the start. The first turn grinds slowly, then fires with a blast of white smoke. The radial engine catches, stumbles, and then steadies into its low-frequency hum, deep, rhythmic, and defiant. Vibration readings remain within tolerance. Oil pressure rises. Exhaust temperature equalizes across both cylinder rows. The data sheet records, operational under duress. Functional margin, extraordinary. The men stand in silence as the OR-2800 roars back to life, shuddering through the scaffolding. Some wipe oil from their faces, others simply watch the needles stabilize on their gauges. According to the subsequent log entry, subject aircraft, damage verified, systems resilient beyond design expectation. Airframe integrity uncompromised despite structural fatigue. Recommend retention for engineering evaluation and field reinforcement model study. When the power is finally cut, the sudden silence feels heavier than the sound itself. The engine slows, then stops in perfect alignment at top dead center. Smoke drifts toward the open door. The Republic Aviation officer closes his notebook. "We built it to take a beating," he says. "We just didn't know how much." By July 1944, fragments from the damaged Thunderbolt are shipped to Republic Aviation's main engineering plant at Farmingdale, Long Island. Each component arrives labeled and tagged: wing spars, armor sections, control cables, even the cracked plexiglass from the cockpit canopy. In a clean inspection bay, engineers in white coats begin the postmortem. Their task is not to repair, but to understand. The P-47's internal design is placed under review. The fuselage frame, originally modeled after Republic's pre-war Sever fighters, is found to have near-redundant reinforcement. The longerons, for aluminum spines running the length of the aircraft, bear stress ratings 40% higher than required by military specification. One engineer remarks in his report, "The Thunderbolt's weakness lies only in the perception of weight." Data from the field confirm it. Of the 2,317 Thunderbolts returning to base with major combat damage between February and July 1944, 92% landed under their own power. Of those, nearly half sustained engine or wing damage that would have destroyed most other fighters. The OR-2800 engine, operating without a coolant system, suffered no catastrophic loss from bullet penetration. Cylinder compression remained stable in every logged case. In the test room, technicians mount a spare OR-2800 to a dynamometer. They drill puncture holes into the oil lines and fire test rounds at non-critical casing points. Even under simulated damage, the radial continues to run for 23 minutes before oil pressure falls below operational range. A note from the test sheet reads, "Failure only by depletion, not by rupture." The realization spreads through the engineering floor, what appeared as inefficiency had become the aircraft's greatest strength. The P-47's excess weight, often criticized for reducing climb rate, provided mass and momentum that stabilized the airframe when hit. Its size allowed armor and fuel protection that smaller aircraft simply could not afford. By mid-1944, Republic engineers begin correlating this data with field reports from the 56th Fighter Group. Photographs show aircraft riddled with holes yet flying formation on return. One image, later circulated internally, shows Lieutenant Robert S. Johnson's P-47 after an encounter with an WWII, 21 cannon strikes, half the tail missing, canopy jammed shut, yet the pilot landed safely. The engineers calculate that the Thunderbolt could sustain structural loss up to 35% and remain airworthy. Reports from German ground crews add context. Captured Luftwaffe documents reference the Thunderbolt survivability with phrases such as "kaum zerstörbar," barely destructible. Technical assessments from the Rechlin test center describe it as too heavy for interception yet impossible to down by short burst. To the German engineers accustomed to precise, weight-balanced airframes, the P-47 represented a kind of mechanical absurdity, a brute force philosophy that simply refused to fail. At Farmingdale, Republic drafts a circular to the U.S. Army Air Forces Material Command. It recommends no major design changes but suggests reinforcing the aircraft's public identity. The memo reads, "The P-47's apparent excess should be understood as design reserve. What critics call mass is in truth insurance." Production data from 1944 supports this shift. Each Thunderbolt requires over 15,000 man-hours to assemble, more than double that of a Mustang. Yet maintenance turnaround averages only 9 hours, less than half that of the liquid-cooled types. Field units report that damaged P-47s can be patched and flown within a day. Spares are modular, and wing panels can be replaced without removing the engine. By August, Republic's chief engineer, Alexander Kartveli, presents his findings to Army Air Forces Command. His briefing opens with a single sentence, "Gentlemen, this aircraft does not survive by chance, it survives by excess." Behind him, projected photographs show the now famous bullet-scarred Thunderbolt that returned from France. Charts follow, engine output graphs, structural stress curves, recovery ratios. The data confirms what pilots already know instinctively: the P-47 can take hits that would destroy any other aircraft in the sky. Kartveli concludes his report calmly. "We did not design for elegance," he says. "We designed for endurance." The room remains silent for several seconds before the commanding general replies, "Then you've given us a machine built for this war." That evening, the test reports are filed under classification code MX 1247. The engineers leave the lab lights on. The damage panels, still scarred with impact rings, are mounted along one wall for continued study. Under fluorescent light, the holes resemble constellations, an accidental diagram of what brute engineering could withstand. By late 1944, fragments of captured Thunderbolts begin arriving at Luftwaffe technical centers across occupied Europe. The most complete specimen is recovered near Laon, France, a downed P-47D with heavy battle damage yet remarkably intact structure. German engineers from the Erprobungsstelle Rechlin test facility record their first impressions in restrained technical prose: construction unusually heavy. Armor thickness beyond fighter standard. Airframe more consistent with light bomber category. The fuselage is placed on trestles in a dim hangar, its silver skin mottled by soot and sand. Engineers in dark coveralls measure the frame spacing with steel rulers, noting that the central longerons are nearly twice the cross-section of those on the Bf-109G. The discovery provokes quiet disbelief. The German philosophy of design, efficiency through precision and minimal mass, meets its opposite. The report continues, aircraft gross weight exceeds 7 tons. Wing loading extremely high. However, structure resists deformation under simulated fire. They fire controlled 20 mm rounds into the detached wing panels. Instead of fracturing, the P-47 spar flexes, absorbing energy. The alloy composition is identified as 24ST duralumin, heat-treated and reinforced by overlapping ribs. One engineer remarks that the American practice of redundant riveting, once considered wasteful, may be a form of passive armor. Comparative trials follow. Rechlin mounts a captured R2800 engine on a test stand beside a Daimler-Benz DB605 from the Bf-109. Both are exposed to gunfire at equivalent ranges. The liquid-cooled inline engine fails within seconds as coolant drains. The air-cooled radial, although scarred, continues running with erratic but measurable power output. Notes from the day's log: radial design inherently damage-resistant. Lack of coolant system eliminates single-point vulnerability. In the adjacent analysis bay, a Luftwaffe officer inspects the P-47's armor plating behind the pilot's seat. He measures thickness, 0.5 inches of hardened steel, then looks toward the comparable section of a Focke-Wulf 190, measuring 0.3. "Theirs is not elegant," he says quietly, "but it endures." Another engineer, more skeptical, replies, "At this weight, no German pilot would leave the runway." Outside, under the winter light, a small group of pilots gather around the wreckage. They run gloved hands across the punctured cowling and remark that no aircraft of such size should still maneuver effectively. According to their written comments, the Thunderbolt's dive stability is unnatural. The dense fuselage generates momentum that carries it through steep descents, allowing American pilots to escape or strike from above without disintegration. German field intelligence begins distributing technical leaflets warning pilots not to engage Thunderbolts below 15,000 feet unless carrying numerical advantage. The aircraft's survivability, combined with its turbo supercharger, makes it lethal in dives and nearly invulnerable when retreating. In combat debriefs, several Luftwaffe officers admit frustration: "We strike and it keeps flying. We strike again, and it still climbs." At the same time, Allied intelligence intercepts fragments of these reports. One British translation circulated through the 8th Air Force Engineering Branch summarizes the German conclusion: "This American machine demonstrates a strange disregard for efficiency, yet it remains operational under punishment beyond expectation." Meanwhile, in the US, Cartvelli's design team quietly takes satisfaction. A memo from Republic's liaison office in London cites the Rechlin report directly. "Enemy analysis confirms our redundancy principle. Structural excess equals survival margin. Field statistics reinforce the point." By November 1944, Thunderbolt losses per 1,000 sorties are the lowest among Allied single-engine fighters, less than half that of the P-38 and a third of the P-51. Maintenance crews note that the majority of downed P-47s are lost to pilot injury or fuel exhaustion, not catastrophic mechanical failure. In one notable case, a pilot from the 362nd Fighter Group is struck by anti-aircraft fire near the Ardennes. His aircraft loses a full cylinder bank and part of the right stabilizer. He returns to base, lands safely, and walks away uninjured. The wreck is logged, photographed, and later presented at a technical symposium as proof of design integrity. Across the Atlantic, Republic engineers compile these operational findings into a classified internal document, Report on Combat Survivability, P-47D and Successor Variants. It concludes, observed enemy disbelief confirms design efficacy. Aircraft durability exceeds psychological expectation. By early 1945, even captured German engineers express grudging respect. One interrogation transcript preserved at Wright Field records an officer's statement: "The Thunderbolt is not a machine of balance. It is a machine of endurance. You could empty your guns and still not be sure it was dead." By spring 1945, the Thunderbolt has become more than a fighter, it is the visible symbol of endurance. Across Europe, its thick silhouette dominates Allied airfields. Mechanics in oil-stained coveralls patch bullet holes with aluminum discs, paint them over, and send the aircraft back to the line within hours. The simplicity of repair becomes its own kind of doctrine. Maintenance records from the 9th Air Force show that 78% of damaged P-47s returned to flight status within 48 hours. A line entry from April 3 reads, "Ship 276 downed for cylinder replacement. Repaired overnight. Airworthy at dawn." Crews grow accustomed to seeing the same serial numbers reappear week after week, their panels now a mosaic of fresh rivets and scorched paint. Pilots regard the Thunderbolt as both weapon and shield. First Lieutenant Glenn Eagleston of the 353rd Fighter Group recalls in his debriefing, "She could take more than I could. I stopped worrying about flak after a month." Another pilot, Captain Walker Bud Mahurin, described diving through tracer fire at 500 miles per hour. "The jug shook like a boiler, but nothing came off." Such remarks, recorded without embellishment, show how confidence became tactical advantage. The aircraft's operational shift begins quietly in late 1943. Initially designed as a high-altitude escort, the P-47 transitions into low-level strike work as lighter Mustangs assume bomber protection. Its mass and durability, once criticized, now serve a new purpose. Over the hedgerows of Normandy and the bridges of the Ardennes, Thunderbolts descend through anti-aircraft bursts that would shatter most airframes. Their radial engines, shielded by sheer metal bulk, absorb hits and keep running long enough for the pilot to complete the run. Combat film from gun cameras confirms this transformation. Frames recovered from the 365th Fighter Group show a single P-47 strafing a German column near Saint-Lô. Flak erupts around the aircraft, black puffs close enough to blur the lens. Yet the footage continues unbroken until the film ends. The aircraft returns to base later that day, recorded as minor damage. Operational planners notice the pattern. Where light fighters require 2 escorts for every strike aircraft, the Thunderbolt needs none. Its capacity to absorb damage changes how missions are scheduled. Fighter groups begin combining escort and ground attack duties in a single sortie. By early 1945, a standard mission includes bomb racks, rockets, and heavy ammunition loads, turning the Thunderbolt into a self-contained assault unit. At Supreme Headquarters Allied Expeditionary Force, logistics officers calculate that the P-47 now accounts for nearly half of all tactical air sorties in Western Europe. Its maintenance reliability allows a rotation rate of 1.7 missions per aircraft per day, an unprecedented tempo. In short memoranda circulated between the 8th and 9th Air Forces, the aircraft is described as the armored truck of the sky. Engineers at Republic take note. Field reports return with precise observations, fewer engine failures, fewer fuel fires, more pilot recoveries. They correlate these with design variables, engine cowling thickness, armor placement, wing spar redundancy. The result is an early study in damage tolerance, a concept not yet formalized but already proven in combat. Photographs from the European theater show Thunderbolts lined wing to wing, their skins patched in dozens of places. Some bear inscriptions painted by mechanics, still flying, second round, old reliable. Each represents a statistic written in steel. When the war ends, those numbers reveal an unmatched survival rate, fewer than 1 loss per 1,000 sorties from mechanical failure or fire. American engineers record the data for postwar analysis. Average combat return rate, 93%. Structural failure under fire, under 2%. Engine survivability after direct hits, measurable in hours rather than minutes. The numbers, plain and unadorned, redefine what air combat endurance means. One after-action summary written by Colonel David Schilling distills the effect: the Thunderbolt was the only plane that gave the pilot more time than luck. By May 1945, with Germany collapsing and airfields across Europe crowded with surviving aircraft, the P-47 stands as proof that brute design could coexist with precision warfare. Its record speaks quietly through the data: sorties flown, missions completed, aircraft returned. At Republic's factory in Farmingdale, the production line slows. Crates of spare parts remain unused. On one wall, engineers pin a map showing every known base where a Thunderbolt landed after taking severe damage. There are over 200 pins. Above them, a single note reads in pencil: 200 holes and still airborne. By 1946, the last Thunderbolts are ferried back across the Atlantic. They arrive at depots in New Jersey, Ohio, and Arizona, sun-faded, pitted, patched, but intact. Rows of radial engines, still gleaming under the desert light, wait in silence for post-war evaluation. The combat reports, the technical sheets, and the German assessments now converge into a single conclusion: the P-47 was not a coincidence of design, but a deliberate statement of engineering philosophy. At Wright Field, the U.S. Army Air Technical Service Command conducts a series of teardown inspections on the final production variants. The findings echo everything seen in combat. The central fuselage tolerances remain within original factory specification. Stress analysis shows no permanent deformation despite hundreds of flight hours under heavy load. One engineer writes in his final summary, "No catastrophic fatigue failures observed. Residual structural life, greater than expected by 40%. Across the Atlantic, captured German engineers under Allied supervision revisit their wartime notes. Many had dismissed the Thunderbolt as inefficient, even primitive. Now, with access to the complete blueprints, they study the logic beneath its bulk." Hans Multhop, formerly of Focke-Wulf, remarks during interrogation, "It is not elegant design. It is design that forgives error." Another adds, "The machine was built to survive its own destruction." Republic Aviation compiles these assessments into a post-war technical digest circulated among American manufacturers. The memo describes a concept not yet named in engineering textbooks: damage tolerance. The P-47 becomes its first proof of principle. Weight, redundancy, and physical margin are reinterpreted not as waste but as reserves, the invisible armor behind reliability. The numbers endure longer than the aircraft themselves. Out of more than 15,000 Thunderbolts built, 12,500 complete their service without catastrophic loss. In Europe, where fighters often returned with wings shredded or tails half missing, survival became a measurable constant. Pilots trusted the machine beyond calculation. For every flight hour logged, the airframe delivered a statistical reassurance that human endurance was matched by mechanical endurance. Film reels stored at Republic's Long Island archive show technicians walking along those battered fuselages, fingers tracing patched metal, counting impacts as data points. Each scar becomes a measurement, a visible equation of what mass, redundancy, and airflow could resist. Engineers reviewing the footage in 1947 begin applying the same lessons to early jet prototypes, the F-84, then the F-105. Beneath each design lies a faint lineage of the Jug's excess structure. In the quiet of post-war industry, the Thunderbolt's noise fades. Yet its engineering signature persists, the idea that survival is not luck, but the sum of deliberate inefficiencies. In military reports, this becomes doctrine: future aircraft must not only fly fast or far, but endure when struck. The numbers from the European theatre are used as benchmarks for fatigue design and stress testing. Every new fighter built after 1945 inherits something unseen, the arithmetic of resilience first proven in the P-47. At Farmingdale, the last operational airframe, serial 44 to 90,368, is rolled out for a farewell ceremony. Former assembly workers, many returning from military service, gather around the massive plane. They touch its dented armor, the repaired panels, the faded stencil on the fuselage, Thunderbolt. No speeches are given. The aircraft stands in silence, sunlight reflecting off hundreds of small rivets. Years later, a single sentence from an Air Force engineering review would summarize its legacy with bureaucratic precision: excess weight contributed decisively to combat survivability beyond design expectation. That phrase, stripped of sentiment, contains the entire story. What German engineers could not believe in 1944, that a machine so heavy, so blunt, could still fly after 200 bullet holes, becomes accepted fact in every hangar where airframes are built to endure. The Thunderbolt proved that strength could be measured not in beauty or speed, but in the stubborn continuity of flight itself. Beneath its dents and scars, the arithmetic still holds: mass equals time, and time equals life.